Good. Okay, well, welcome everybody. Thanks for making it out. I know it's a little bit slippery out there, so we appreciate your coming out for the event tonight. For those of you who have never attended one of these events before, my name is Brian Jackson. I'm a faculty member here in the physics department. I teach physics and astronomy. You are attending the Boise State Physics First Friday Astronomy program. These take place on the first Friday of every month, all throughout the calendar year. All 12 months. Sometimes people ask if the university is on break, do we still have these? We still have these. I still make my students come in over break. They take place first Friday of every month, 7:30 p.m. We're doing them in this room for now, probably for the foreseeable future, but they are also live streamed. So if you can't make it down in person, you can visit our live stream, boi.st/astrobroncoslive. There's some QR codes in the back as well. That'll take you to our YouTube channel, where you can live stream not only this talk, but you can actually see talks that we've had going back, I think, 3 or 4 years now. So there's a nice catalog of talks going back several years. Usually, well, assuming good weather, after these talks, we go out and do stargazing on the quad, which the quad is just that way from here. Unfortunately, of course, it's cloudy out tonight, so won't be able to do that. So stay tuned. Come back again, and hopefully we'll have a chance to do some stargazing. We've also begun a program of stargazing every Friday night, again, assuming the weather cooperates. So if you're looking for something new on a Friday night and it looks like it's clear and not too cold, check out our website. You can just Google Boise State Observatory, and you'll find information on the website there, and it'll tell you whether we're going to stargaze that night or not. These programs are entirely donor supported. So the cost for bringing the speakers out and putting them up here in Boise is paid for by you all. And so if this kind of programming is something you really enjoy, would like to see more of, we urge you to visit our website where you can make donations, boi.st/astronomy. A QR code again is available at the front desk for donations. It's about $1,000 a speaker to run these events. So just, consider that when you're thinking about making donations. And so our guest tonight, we're very fortunate to have Dr. Christopher Moore here from the Harvard CFA. Dr. Moore has a PhD in astrophysical and planetary science from the University of Colorado. Before that, had a master's degree in the same topics. And then before that, a bachelor's degree in physics from the University of Iowa. He is currently a staff scientist at the CFA, served as a postdoc at CFA before that, served as a research assistant at Boulder as well, and then as a NASA intern, I guess way back in the day, huh? Back at in Goddard Space Flight Center in Greenbelt, Maryland. He does a variety of different kinds of research, and we're going to hear today about his work on satellites. I think you're really going to enjoy it. We've had a really enjoyable time today talking with him during his visit to the university. So with that, let's welcome Dr. Christopher Moore. Okay.
Do a sound check. Can everyone hear me? Cool. Well, thank you all for coming out to the first Friday for February. Like Brian mentioned, I am a researcher at the Harvard Smithsonian Center for Astrophysics, and I'll be talking to you today about launching astrophysics telescopes and detectors on rockets and small satellites. Before we get started, by show of hands, who here has seen an actual rocket launch before? So we're like 7 or 8 people. That's pretty good. You haven't seen one yet?
From afar, way far.
Okay. Well, you'll see a few today. So maybe it's good enough. It won't be as good as in person. The people here in the audience can attest to that, but it should be the closest you're going to get. Okay. Because you're going to get a front row seat to a rocket going up to space. Okay. So what we have here on the screen right now is a CubeSat that I worked on as part of my PhD work. And this CubeSat was deployed from the International Space Station. I'll discuss it in more detail a little later in this talk. So more about myself, there was a quick summary given. Right now, our research group and my main interests are studying the solar atmosphere. Now, I didn't start off saying I want to study the sun because we see it every day. And it doesn't look that extraordinary, right? What I did want to study initially were O and B stars, These are the hottest, brightest stars. I thought they were very cool, but I did a summer internship at the University of Colorado while I was an undergrad, and I had an opportunity to see the actual satellite data coming from the sun, and I saw it in exquisite detail, which you will also see later today. And that, coupled with me seeing the instruments actually in the lab at Colorado as an intern that took the data, fascinated me. And then I made a pivot in terms of focusing on stars very far away, which appear as small little dots in the observations that are taken with our current observatories, including like the Hubble Space Telescope, to the sun, which is much closer, but then it allows for an extraordinary view of its dance that it does in the sky almost every day. And sometimes we don't see it because we don't have the lens or the filter to correctly observe some of these phenomena that I will show you today in ultraviolet light and in X-rays. So we see pretty cool dynamics, but we want to see them even better in higher definition. So our group also focuses on the development of X-ray detectors and ultraviolet detectors and mirrors to get higher quality observations. So at the University of Colorado in grad school, I worked on the development of UV coatings and the miniature X-ray solar spectrometer CubeSat. For those of you online, I'm using the cursor to point. But that's a photo of me back in grad school holding one of two CubeSats that I worked on intimately in grad school. There were three in total, miniature X-ray solar spectrometer CubeSats. And the first two I worked on directly every day in grad school. So what is our main focus in the high energy solar instrumentation group at the Center for Astrophysics? It's primarily constraining the quiescent. So this is non-eruptive, non-transient phenomena, and the eruptive heating processes in the atmospheres of solar type stars. And we're using the sun as a proxy and as a baseline for all other stars that are similar in mass and size to the sun. We do this in a multitude of ways. We first focus on developing the technology. One example of this are detectors that are improved with our group. We then implement these new detectors, mirrors, gratings, etc., into instruments. So this is a combination of these things to create high quality observations. We have to put these instruments on certain platforms, which I'll be discussing today, such as CubeSats, small sats, and rockets. They acquire data. We do modeling in our situation on the atmospheres of stars, mostly the sun, but we do a little bit of stellar atmospheric science. And then we can corroborate the observations and compare with our theory, our simulations. So these are physics equations. You modify them so that they can be put on a computer. You use the computer to solve them and evolve the equations to create an almost realistic scenario, in this case for the solar corona. And that comparison says, how well are we doing in our understanding of fundamental physics? And that provides a point where we can go back and iterate and start back here at technology development, and then it can go over to simulations. It doesn't always have to flow this way. Sometimes it flows from the right to the left. But one of the main reasons it's more effective to flow the way I just mentioned it is because astrophysics is highly driven by observations. As an example, how many of you heard of gravitational waves before the discovery was made? About 9 to 10 people, exactly, right? It was theorized and observations were created or detected to see it. But that's not always the case, where Einstein said, hey, something should happen, and then all the scientists rush out to take about 100 years to detect it. Sometimes we see a phenomena, we observe a phenomena that we couldn't have fathomed before. And that drives our curiosity, and we push our understanding to better constrain what physics are driving these phenomena. That's most of the time it happens in that way. An observation happens of some crazy phenomena, and then we try to go understand it. It's not always like Einstein said something, and then we go rush to prove it. But that's been happening recently. So Einstein was the man. I wish I have a career anywhere close to Einstein's, because he's got like a 4 for 4 hit rate. So I've been talking about stars, but I cannot assume everyone in the audience has been thinking about stars all day, because you guys don't. You have busy lives, right? Us astrophysicists, we literally sit around and ponder all day about stars, galaxies, black holes, neutron stars, supernovae. So to make sure we're all on the same page with some basic language, I have a diagram of the zoology of stars here. On the vertical axis, we're showing the brightness of the star, the intrinsic brightness at its surface in visible light. So brighter is at the top, dimmer is to the bottom. And going from left, it's hotter stars. These are the O and B stars that I said I was most interested in. They're the bluest, most massive. Because they're so massive, they burn through their fuel very fast, very efficiently. And they live these extravagant lifestyles and they die pretty fast. Kind of like stars in Hollywood sometimes. But on the right side, we have cooler stars. They're less massive. They burn through their fuel less efficiently to some extent, and they live much longer lives. As an example, there's times here, it may be hard for you to see, but the lifetime here is about 10 million years. On the right, the lifetime here is about 100 billion years. So that's 10,000 times longer in duration. And these stars are kind of boring. At the surface, there's a pun there. The atmospheres are not boring. It's actually interesting and ironic that the atmosphere of the stars on the left are kind of bland and mundane, but the atmospheres of the stars on the right are highly dynamic, highly active. They lead to eruptions that you might have heard of, like coronal mass ejections, which all stars have material leaving their surface and flowing out into their local stellar spheres. But the way it happens on the stars on the right is highly volatile. Now, the stars on what's called the main sequence follow this pattern that we see here. This is mainly when stars primarily form hydrogen into helium, nuclear fusion. And as this process evolves, these stars migrate over to the top right. And eventually they can end up, some of the lower mass stars, like the sun, end up in the bottom left corner as white dwarfs. Some of them end up as neutron stars, and some of them end up as black holes. Mostly the stars in the top left will end up as black holes, which most people have heard about. And this is called the Hertzsprung-Russell diagram. Two individuals that essentially devised this type of way of displaying this information. And the sun is located here, and it's on the right side. So expect the dynamic, crazy, volatile atmosphere. And because of this, I think the sun is one of the coolest stars in the sky. And I'll show you why. So in general, a quick discussion on the interior of stars. Because the interior of the stars has a huge ramification for how the atmosphere will be. I kind of told you that the atmosphere is dynamic for low mass stars, the cooler stars. But let's talk a little bit about why that's the case. Essentially, what drives the dynamics of the fundamental physical processes in stars after you have the nuclear fusion in the core? It's a competition of how efficiently the star can have energy propagate radially outwards toward the surface. So the star, it's kind of cool how this happens, kind of knows, which is like most nature, the best way to do this. And low mass stars, it does this by literally moving fluid. It's called convection. So hot fluid material rises, cools, and drops back down. But over time, energy transports radially outwards. This happens in the sun, but not into the outer layers. And in the higher mass stars, this happens near outside of the core. Now, for various reasons that I won't go into any detail now, but you can ask me later, the way that the light's absorbed, it's efficiently absorbed so that energy by light transfer is not efficient. Then you get convection as the primary mechanism that happens here and for these high mass stars, and then radiation, just light streaming outwards in the higher layers of the interior of the star for the high mass stars. That does not happen at all in the low mass stars. That does happen in the sun here. And as you get to this point, there's an element called helium. You get electrons binding to it. The photons are really efficient at making that extra electron that bound to the helium atom be released again. So it's really inefficient for light to propagate that energy outwards. So then you get convection. Now I'm saying all this to say, there's going to be something really cool you're going to see, which is a consequence of this. This is another view on the left-hand side of the atmosphere of the sun compared to the interior. So we talked about the core, nuclear fusion's happening. Then we have radiation primarily transporting the energy outwards. Then we have fluid motions, convection here. And that leads to a dynamic, crazy atmosphere, which has this weird structure and temperature. On the right-hand side, I'm showing you a plot. I know there's a lot of plots, but after we get through these first few slides, there'll be less plots. More cool videos. The vertical axis here is temperature. This is 1,000,000 Kelvin. Or you could think about it as roughly 1,000,000 Fahrenheit. It's close enough for this talk. So at the surface of the sun, we're down here at like 6,000 Kelvin, 6,000 degrees. And as we go towards the higher layers of the atmosphere, towards the right, it shoots up to over 1,000,000. So this region here is over 1,000,000. Why? We're not really sure. This does not happen with those hot, very massive O and B stars. Their atmospheres do not seem to do this right now, with all the evidence we have from the observations. But for stars of the mass of the sun or lower mass, this process occurs. It's called a temperature inversion. I told you these atmospheres are crazy. That's the first weird effect that we see. Again, observations can drive astrophysics. People didn't sit around with pen and pad and say, oh, this should happen. It was like, oh, we observe it, and we're like, what is going on? So we devise all these instruments that we put on these payloads that you'll see with rockets and satellites to get higher quality observations. And this is why I haven't gone and studied O and B stars yet, because I saw things like this and I said, man, the sun is so close and we can study it in great detail. So before I even go back to O and B stars, let's try to further investigate the fundamental physics that's happening with our own star. That's literally right there. And because it's right there, when we have visible light observations on the satellite, so we don't have cloud coverage, we don't have to worry about the Earth spinning. We can stare at it for 24 hours continuously. It looks like this. Does it look interesting to you? I hear chuckles. So it seems kind of boring, right? Like I said before, you're like the sun, it's there every day. Why do we care? Well, it looks pretty boring. And in the bottom left-hand corner, just for context, before I focus on this black box, that's Earth. So that's how small we are compared to the sun. You can fit 100 Earths across the diameter of the sun. And if we focus on that little box, this is what we observe. And this is part of the reason I made a conversation about granulation, sorry, convection. We have granules. And for me, I can sit around and watch this all day. It's hot gas in the center and cool gas in these darker regions. And there's these bright things here. So what's going on with these bright things? Well, there's not enough time to talk about them in detail today. You can ask me at the end. It may come up a little later. But like I mentioned before, this is the surface of the sun, and this is convection, thinking of like a pot of boiling water. Hot fluid rises, it cools, and then it flows back down in a darker region. And these granules are all across the sun. So if we go back, we look at the sun here, they're everywhere. When you zoom in, you have spatial information in much more detail, you see this. So not just the surface of the sun has these effects. When we look at the outer atmosphere, it gets even wilder. Has anyone here seen a solar eclipse? Wow, this is really good. This is more than 60, 70% of the room. So the solar eclipse that I've seen last, it was in 2017. I did not see the 2024 one for a reason I'll tell you in a little bit. We had a rocket to launch in Alaska, so we missed it. But here's a video of that solar eclipse. And when the moon occults all the light from the visible surface, you see the outer atmosphere. You see all this light coming from these regions here. Most of that light's actually scattered from light that came from the surface. It's scattered off particles that are in the atmosphere. And then it comes towards Earth where we detect it. And when you take a long exposure, and this part here was actually, this part of the moon was superimposed, but all of this is actual observation. These are charged particles, free electrons that are confined to follow the large scale magnetic field structure of the sun. Sun's a big ball of hot gas or plasma, and that creates magnetic fields. These magnetic fields drive all the dynamics and all the things you're about to witness for the solar atmosphere. I think this is pretty cool. And this is what we see in visible light. And I keep saying visible light, ultraviolet light, X-rays. So again, to make sure we're all on the same page, you can envision this red wiggle here as the wavelength of light. for a physical distance, how does the strength of the electric and magnetic field change? And that corresponds also to a frequency or energy. So more changes, higher energy, less changes over a distance, lower energy. The visible lights here, we'll be spending a lot of time down here in the ultraviolet and the X-rays, which are more energetic. And many of us have experienced getting X-rays at the doctor. But when we look at the sun, instead of invisible light, and we look at an ultraviolet light, it looks more like this. Does that look similar to what we just saw in visible light? Oh, it looks very different. And those regions that were little dark spots that we call sunspots, they now look bright. Those are these things here. Those are strong collections of magnetic field that extend out into the surface. So right now we're looking at 3 different windows of ultraviolet light, and we've made a composite, and then we're watching this over time with satellites in space. And you also will see these flashes of material shooting out. Those are coronal mass ejections, and they're also solar flares, big eruptions. The sun is doing this almost all the time, and we don't see it with our visible eyes. Like I mentioned before, we need the right filters or the right lenses to see the sun in a different vantage point, a different viewpoint. In this case, this is in different electromagnetic spectrum, different color of light. And the sun is highly volatile, highly variable. And again, this is not the same case for those blue B and O type stars. So if we take, those are actual observations. And what I'm about to show you right now is, again, actual observations. It's not made up movie, it's not sci-fi. These are satellite images of an eruption, a solar flare with a coronal mass ejection in the atmosphere of our star. And there are different colors you see here. The red and the black are cooler gas. The white is hotter gas, and the purple is the hottest gas. And this amazes me every time. So you saw material be shot out into space. You're seeing cooler gas come back down into the atmosphere. And if you watch close enough, you can actually see the material follow these patterns of the white magnetic field structure that is being depicted here by the charged particles following the magnetic field lines and then losing light that we're detecting. That's how we see it. We're not directly measuring the magnetic field, but we can infer it by the pattern of light emitted from the gas along the magnetic field. Do y'all want to see this again? So we have a resounding yes. So we'll play it again. And again, I could watch this all day. But these type of phenomena are occurring all the time. So it's amazing what we see when we have a different set of lenses, a different set of eyes. To me, it kind of reminds me of lava. And you actually see magnetic fields here. They're going out and then they're coming back into the atmosphere. And that can lead to instabilities. And when there's enough tension there, like a rubber band, it can snap. And that snapping shoots plasma out into space and also plasma back into the atmosphere. And what you're seeing here is primarily what our group studies, using data like you're observing here in ultraviolet light. But we also use X-rays. So that was UV light, and here's extreme ultraviolet light to probe the different temperatures of gas. And the hottest gas is in the bottom right corner. You see it's most tightly bound in the core of these hotter regions. They're called active regions. And if you go to cooler gas, 1 million degrees Kelvin, it's more spread out. But you still see a pattern. That pattern is most readily apparent when we look in X-rays. So as we go across the electromagnetic spectrum to higher and higher energy, we're seeing different phenomena in greater detail. The sun goes through these cycles where these magnetic fields pop out. They emit a bunch of UV and X-rays. They make these flares, these coronal mass ejections every 11 years, and then the cycle goes away and repeats. So every 11 years, you have a peak. And about 6-year time frame, you have a lull between these peaks. And so that's what you're seeing here. So our group studies this. So that's why soft X-rays are pretty important. The hottest plasma, like we just said, are in these bright regions that are observed in X-rays. And they are highly variable, highly volatile, and dynamic. So we have to go up to space because Earth's atmosphere, it gives us life, but it's got nitrogen, it's got oxygen in it, it's got argon in it. A lot of these molecules absorb a lot of UV and X-ray light. That's here on the left. So to see this better, we got to go to space. We're fortunate in invisible light that there's a window here where the light passes through most of those molecules. But for X-rays and UV, we got to go to space. So our main rides to get to space are the main topics for today. CubeSats, small, very, very small spacecraft, rockets, and large satellites. And when I say large satellites, I mean like the Hubble Space Telescope, which is about the size of a school bus, or the Chandra X-ray Observatory. So these are really, really big satellites. Two projects that I was a part of, one in grad school, now as a researcher, are working with new detectors. Spectra, which is how much light you get as a function of color, and also fast imaging. So quick dynamic detectors. And I'll be talking to you today about these two projects, the MINX and DAX CubeSats, and also the High Resolution Coronal Imager, HIC, and Swift Solar Activity X-ray Imager. A bunch of acronyms, right? Acronym soup. SAXI rocket. We'll start with the rocket because people like rockets. So to win money from NASA to put a new detector into space, you need a science case. So first you have to address a need that has not been addressed before in terms of performance of the equipment. And then that has to give you information that's new about a physical object, astrophysical object. In this case, for HIC and SAXI rocket, the colored segments here, we're reading out we have very fast time cadence images, factor of 10 to 100 times faster than anything already in space, which are the gray here. That's the motivation. Our group trains the next generation. Here are some of the junior scientists. These are postdocs. These are grad students. These are undergrads that are in our group. And we've developed this technology. We put it on a NASA sounding rocket. Here are a list of some of the rockets, and it's actually hard to read, but the one near the middle here, a Black Branch 9, is the one you're going to see shown in these videos. It's pretty tall. It's about 60 feet, and it goes pretty high. Question is a trivia question coming in. The question was, can you hit the International Space Station with the sounding rocket from NASA? What do you guys think? By show of hands, can I get a yes, you think you can? Shoot one of these rockets up and it can go high enough to hit the International Space Station. You're right. But you have to make sure that you don't put too much weight on it. If it's too heavy, it won't get there. But if you have just the minimal amount of weight, it can get there. And that's what this graph is showing for different versions of these rockets with different weights. So this horizontal axis is the weight. It tells you how high you can get. The ISS is about 400 kilometers, which is right here. So a lot of these rockets can get there, including this Black Branch 11. It gets 4 times as high as the ISS. So just think about that. And these rockets are actually spare from the military. So think about what they have that's not spare. And here's a shot of one of the rocket's path going up into space. This is actually from Alaska. And you can see what you will see in the video soon, the first stage break off. And here's the second stage igniting. That's why the light looks a little thinner there. And so what you all been waiting for, your first main video of a rocket launch, right? So in grad school, in my first year, I was part of an astrophysics group, and I helped with this rocket that you're seeing being turned vertical right now. It has a telescope on it to measure the atmosphere of ultraviolet light coming from the atmosphere of a star. And what you see is a styrofoam box here, which is meant to keep the scientific payload cold. And because we're in White Sands Missile Range, New Mexico, and it's actually like 80 to 90 degrees, so it's pretty hot. We want to keep the instrument pretty cold, like minus 50 degrees Fahrenheit, roughly. And so this video is going to show you a nighttime astrophysics launch and the sounds that the rocket makes when it launches. Compared to the big rockets that launch satellite, like large satellite missions, these rockets shoot off the launch. So if you blink, it's gone. You turn your head for a second or two, you're going to miss the launch. And that's how quickly they get up.
That's 10.
And that's the second stage igniting right there. So I'm going to skip ahead to see the slow motion because we have more videos to check out. And this is what it looks like in slow. Styrofoam box apart. And it's pretty cool because you can, the whole desert range lights up because they're so bright. You also have to be careful. If they go off to the wrong path, there's a termination system that separates the scientific payload from the rocket boosters. I've also had that happen. I've been part of 4 rockets. 1 was terminated, the other 3 were successful. Pretty cool, right? So that was at nighttime. What about during the day? So this rocket, I was not a part of, but I was a part of one later. And it's the launch to see the sun. So here, my man up front, he's about to ride along the rocket. We have cameras forward and aft, so in the direction of propagation and backwards. And we're spinning for stability. Because if you don't spin, you'll nose cone will wobble, and that changes its path every time. So you spin, it's focused like no momentum. You see here how long the spin since launch. You see the speed, you see Z forces. This is our parabolic trajectory. We shoot up into space and we come down. This rocket goes about 320 meters because we were kind of heavy. So we don't go up to the ISS, which is 400 kilometers, 400 kilometers. And if you notice, you don't hear anything anymore, do you? So most of the air is left. And so now there's not really an efficient medium to transport the sound. Sound is mostly airwaves or just particles hitting each other, and then your eardrums detect that. So there are not many particles, so you don't hear much sound in the microphones on the video camera. So eventually, we stop spinning. The second booster comes off, and then we swing towards the sun. The door opens. You see the door here for the payload, and then we'll start taking solar observations. And then we do this for about 6 to 7 minutes. Then we start coming back down. So I'm going to speed up to re-entry, only because we don't have all night to be here. But I'm sure you'd want to stay all night and watch the rest of this, right? And trust me, it's very exciting when we're doing this live. We're actually pointing the rocket. It's like a little video game panel, and you have to tap where you're pointing and hit the button, and it slews. It shoots out gas, and it points itself. And if you point the wrong direction, because you do have live feed, telemetry down, you have to quickly fix where you're pointing. And you'll notice you'll start hearing the air coming back into the payload. And we're tumbling intentionally to distribute the heat. If you don't do that, and my first PhD advisor at Colorado, his rocket actually heated up on one side because they had a malfunction and it did not tumble, and the whole rocket bent in half. Because metal expands differently as a function of temperature. Hotter temperature expands than cooler. You got that temperature differential. Those forces cause the rocket to bend in half. This PhD project was gone, but that was bad. But he told me that would never happen to me because he would make sure I wouldn't. So the rocket's coming back down, and I'll speed up to parachute being deployed, and I think we don't have that here. Sorry. But the parachute deploys and it eventually lands. Now the rocket that I've been a part of 3 rockets, successful, 1 cut down. The last one that was successful was a year ago. We were in Alaska to measure a solar flare with EUV and so extreme ultraviolet and soft X-ray instruments. I'm PI for the SAXI rocket instrument, and I was part of these other instruments here. High resolution coronal imager. You're going to see some images in a second. Kool-Aid, pretty cool names, right? Capri Sun. We were told to call SAXI Sunny D, and I said we could do it, but the team was like they didn't want to do it, so we didn't. But that would have been a complete juice package, right? But you can see the mirror for high C, which is a 2-mirror telescope back here. This is the reflection off the telescope tube here. The secondary mirror is here. Kool-Aid is an instrument here. SAXI's over here. We are protecting them right now with covers because we don't want them to be contaminated. Like I mentioned before, we launched it from Alaska, 2014 in April of last year. Black Brant 9, now you know what that means. There was a bunch of testing that we had to undergo. That was at White Sands Missile Range in the desert. We tested the center of mass, center of gravity, vibration testing, where we shake the crap out the rocket, make sure things don't break before we actually launch it and it shakes for real. Telemetry, make sure we can communicate, GPS, pointing. We put the rocket horizontal before it goes vertical. You've seen it go vertical. There were two rockets, actually. Another rocket is an X-ray rocket called Foxy. They launched first, and 1 minute later, HI-C, the ultraviolet and soft X-ray rocket, we launched second. Here's a photograph with most of the people that were physically present. It's over 200 people that I counted in this photo, which is only half the people that were necessary to accomplish this. It's about 400 to 500 people that worked diligently over 3 to 4 years to make this become a reality. So we thank them for their hard effort just to do the science, right? This is all for science, to study the sun, right? Some of the other members and myself are here. Got a little Photoshop. Now the sun in ultraviolet light looks like this. There was a big eruption, a flare, solar flare that happened here, hence the peak in this intensity of light over time. This blue region is where we actually had our observation. The first rocket had already launched. This is HI-C flare, the second rocket. And it was cool to see that, but let's watch this slow-mo. It's pretty slow. But in Alaska, as you saw, the entire rocket's in styrofoam. That's because in Alaska, it was like 0 degrees to 40 degrees Fahrenheit, basically every day. And we had to keep the rocket at this constant temperature range, rough constant temperature range. And I never get tired of watching this. One of the reasons we had to go to Alaska to launch this rocket is because we were literally sitting every day waiting for the sun to have a flare. We have satellite observations that are consistently monitoring the sun, and we have that information piped down to us, and we're watching the monitors on the screen, waiting for the right type of eruption to occur, and then we literally give it the trigger to go. And everyone's sitting there waiting for about 6-7 hours, armed with the rocket ready to launch, and we literally wait. And it took a few days to finally get to this point, which was well worth it.
Here we go. There it goes.
As you see, they're really fast. So that was someone on the missile range with their camera. And here's a slightly better photo. And they're really loud, and you can actually feel it in your chest. So HI-C flare took data, like we said, high resolution coronal imager, extreme ultraviolet images. That's what you're seeing here. Some of the data is not fully processed yet, but this is what we currently have. Now, flare, these are strong magnetic fields. They've rearranged themselves. They've heated up gas. They've made a bunch of light. They shot out particles into space and have particles also pushed into the solar atmosphere. And that's what you're seeing here is the remnants of that. It's still going, but the time cadence is so fast. It doesn't look like much is happening. There is a brightening that we observe here. But here's the raw science data before it's fully processed to look kind of like what you saw in those other videos. It doesn't come out beautiful initially. We have to do some massaging of it, and then it comes out pristine. So that's the HI-C, SAC-C rockets. Now let's talk about CubeSats. If you've heard about them, they've been the craze for about 10 years to 15 years for science observations. And again, to get money from NASA, you have to address a need. The need at the time was there weren't many measurements in soft X-rays that covered a whole bunch of different colors. It's called spectra. That's what the MINX CubeSats were designed to do. This red region is saying, over this time frame, there were not many measurements that took spectra. The vertical axis is different colors of light in the soft X-rays. This yellow box is saying, hey, MINX 1 and MINX 2, they're designed to do that over this time frame. So let's make it happen. We're addressing a need. There weren't any other boxes here. We put the boxes there. NASA says, we think that's a great idea. Here's some money to go make it happen. And at the same time, you're going to train the next generation of students and postdocs to lead the next versions of missions. And that's what we did. At the time, Charlie Bolden was the NASA administrator towards the tail end of my graduate career. and he showed up to Colorado. This all happened at Colorado and Boulder, and he was impressed with what we did. Here are some of the team members. There have been over 50 plus graduate students that have worked on the Minx 1, 2, and 3 CubeSats thus far. And here's what they actually look like. You saw it with me holding it. So you see how small it is. It's like this big. They're tiny. And our team, with help from others, in terms of the pointing system, we actually built and designed everything you see here. My job was the scientific instrument, so the detectors, the filters, data processing, but other team members, other grad students worked on solar panels. They worked on power systems, command and data handling, telemetry, data downlink. Here's an example of one of our detector systems that I worked on. And they're small, but they are fully functioning satellites. It's kind of amazing. Here's a computer model of Minx. You saw the real thing. And our antenna is literally measuring tape. Believe it or not, it works. To make radio waves, all you need is metal, or you need electrons moving back and forth, or charged particles in a pattern, and you can generate radio waves. And that's what we did, like literally. It's pretty cool. But before we put it in space, like you saw with the rocket, we have to test it. Now, unlike some of the rocket testing, we actually can't show live video of that because it's at a missile range, and that's not proprietary, but it's connected. Well, for this satellite, I can show you a video that we make because it's for academic purposes. So there are a lot of testing for our satellites. We had to thermal vacuum test it. What does that mean? We made the temperature hot and cold to simulate being on orbit. Make sure that all of our systems perform nominally, and if there was an issue, an anomaly, we had protocols set in place to address it. And we tested those protocols. One thing that's a big issue that's end of mission or dead on arrival is your solar panel is not deploying. So we have wires, and once we get the signal that we should be deployed, there are some wheels that are compressed, and when they're not compressed, they come out, they heat up the resistor snaps the wire, and that worked. Now we're testing if we can point towards the sun with our camera system that are visible light that are provided to us by a company called Technology. We were the first flight. They had never proven it. They proved it with us. Here's we're trying to deploy our measuring tape. And that was me back in grad school. You know, like supposed to go up, but it went to the side. We also did the same deployment in vacuum. Friction around the lower. Measuring tape will not deploy. We had to verify that was the case and it would deploy. So here we're testing the pattern of our radio waves. Make sure we understand that communicate effectively and receive from our So again, it's a small CubeSat, but we have some fancy tests. These are tests that large satellites. Now we're testing how precise we place our photon. We had a Yagi antenna, ultra high frequency, 437 megahertz roughly, the frequency that we got cleared just for us, narrow band. And James Mason, who's a PhD student in aerospace, a senior by a year at the time, he's placing these solar panels on here. He was in charge of that part of the project. I was a scientist, so I was in charge of the science instrument, data doing the science analysis. But there were many other aerospace. I was astrophysics grad student. There were aerospace grad students doing something. Now we're doing reverse bias on the solar panels. So instead of collecting energy and spitting it out, you should be able to absorb the energy and heat up. They have nowhere to go and radiate infrared and red light. Unfortunately, we had, for Mix 1, we had multiple issues. It tends to happen when you're building a satellite. And we had to reassemble Mix 1 like 4 times. This is something you do not want to do. Because every time you disassemble, you break something. Every time you reassemble, you break something. So now here we're testing our X-ray instrument at a light source that comes from electrons that are moving towards the speed of light. It's called a sequence. We did that test and then we can detect X-rays with our. Now we're testing when we come out the deployer, do the solar panels pop out accurately. And Brick Corner right here actually built this air-bearing table himself, pouring nitrogen gas, and it keeps us balancing on that half sphere. And here we have silver tape that's used to reflect light, so we don't absorb it and make electrons that can cause interference with our electronics. There's Greg. He was really excited to do that kind of thing. We also have to make sure the solar panels are pretty clean. We don't want to contaminate anything else on the rocket or on our CubeSat. And when I say the rocket, there's a big rocket you will see right there. At Colorado, there are a few professors that are former astronauts. We had a little party before Minx 1 was launched. And we didn't have anything for him to sign, so we signed the box. And we also had our names engraved on all 3 CubeSats. So our names are fixed. Not anymore for Minx 1 because it's fun. Minx 2 and Minx 3 are still up in space taking data now. And they're conducting high quality science observations. So for the launch of Minx 1, back then I had like a little mini fro. We were really happy at Kennedy.
4,
and this
3,
is the big rocket. So
2,
you'll notice the difference
1.
in the time it takes this rocket to get off the launch pad.
Liftoff.
And this is probably what you're more familiar
On
with.
the shoulders of Atlas, the SS Deke Slayton II orbital ATK Cygnus spacecraft soars toward the International Space Station.
This was a great day.
Q has gone closed loop control.
I watched my thesis project go up and it didn't blow up.
HRL roll programs and gun fire rates look good.
That does
Listening to
happen.
Marty Malinowski.
3180 pump speeds and jerk pressures are abandoned.
So before this
Send it
launch,
mark.
there were about 3
Fire rates
launches,
continue to look
two
normal.
of them I think SpaceX did, where they had CubeSats on board with flags at the time. And they actually, so we were kind of nervous at our rocket.
42 seconds into flight.
Things were great.
New rates climbing somewhat, so we're controlling well. 3180 pump speeds and jerk pressures all look good.
So our CubeSat was launched up into space, went to the International Space Station, where it sat in its
Flying the zero
foyer
angle
for
attack
about
phase of
6
flight.
months. And
HRL
then around 3 in the morning Mountain Time, it was deployed. And we had to have astronauts actually execute this deployment. And it was really, really, really early in the morning, 3 a.m. And astronauts don't care, right? It's 90 minutes for an orbit. They are on their own schedule. So we had to be there and wait in an auditorium like this. And right after it was deployed, get ready to start executing our commands to telemetry with that Yagi antenna that you saw up into space to our CubeSat. So when I first saw this, because it was 3 in the morning, I was like half sleep, right? So I was looking, I was like, oh no, it's gonna crash to Earth. Because that's how I actually like looked. And I was done, my physics brain took over and I was like, oh no, we'll be okay. We're gonna orbit, it's all good. But we're actually deploying down and away by a meter a second, differential in velocity from the ISS, so we don't come back around and actually impact the ISS. So that's why it looks at that angle. And thanks again to astronaut Tom Peake for taking these amazing photos. And he took many more, which I'll share with you here. And these are very high resolution, high quality photos from the deployer arm that was used on that day. It's pretty cool, right? It's amazing how dark space is compared to everything else. And how beautiful Earth is. See cloud coverage, see snow. It's just beautiful. So that was us on the roof trying to make sure this antenna worked. There were long days, arduous work, but it worked. We got data, science returned. NASA liked it so much, they did a special for us. Now, here's an example of the pattern that Minx followed in its orbit. And if we're looking at from Earth's perspective, what our orbit looks like for Minx. We had about 4 to 5 passes a day, and they lasted about 10 minutes. We can communicate with our CubeSat, and the CubeSat could send data down to us. And at the time, it's all automated now, but when we first did it, it had not been done before in this way. So we had to show up. And the passes will occur any time of the day, any time of the night. So we had to be there. And we took turns. And now if you look at the frame of the sun, and this is sped up, highly sped up, but Earth is spinning underneath, rotating every day. And then our orbit is precessing around as Earth is revolving around the sun. And like I said before, we took high quality science data. On the left-hand side, this is the amount of light detected or counts as a function of energy of the photons on the horizontal axis. The different color lines are different conditions for the sun. The sun has a flare in the black. It was very quiet and not many flares are happening with the blue time frame. And this isn't the highest quality, nice lines, but before these observations, there weren't any before in the spectral range. So that was the first thing we did. We proved with our CubeSat at the time that one could take a fairly low cost detector, modify it slightly, put it on this small little device, the spacecraft, and it can operate successfully and create science quality observations that scientists across the world can do science with. So that was a big deal at the time. And so NASA made this video for us on the right. So that was a great experience for me. And I hope this talk has been a great experience for you. As you've seen the CubeSat, you've seen sounding rockets, and you've heard about technology and the journey of myself in my academic career in terms of finding my dreams come true in science of the sun. And I hope you all can make your dreams come true in your life every day. So thank you for your time.
All right, who's got some questions? Right here.
So you had mentioned that with the rockets, you have styrofoam around the actual payload to keep it cool. How do you keep it cool when it's like going through the atmosphere? Because the styrofoam fell off, didn't it?
It did fall. We broke through the styrofoam. We bust through it. Great question. So the question for folks online, yeah. So for everyone online, essentially the question is, how do you keep the rocket scientific payload cool as it's moving upwards into space, right? After it's gone through the styrofoam, broken through the styrofoam box. We do the best we can to keep it as cold as possible, a little bit colder than what we want it to be when we're actually making our observation in space. The observations are fairly short. They're about 10 minutes, and it's thermally isolated. So we have multiple layers of rocket skins, and actually in the outer layer of skin, it's actually a vacuum seal in between it, and then between that vacuum seal and the outer layer, there's actually air. And air is a really good insulator. So we cool it internally with liquid nitrogen, and we make sure, because it's sitting there literally all day in the desert sun for white sands or in the cold in Alaska, we have a particular temperature we want it to be at. And so after we cool it internally, the styrofoam is to make sure no external heat flow comes in from the sides. Now, great question. When we're going up, it does heat up. The outer skin heats up dramatically. It goes over to like 100 plus C centigrade. But the insulation keeps it from rising too fast. On top of that, we have a thermal link. So we have metal connected to vital components. And there's a big block of copper or metal that's sitting at a certain temperature that helps minimize the temperature rise. But the temperature does increase. But we design and test everything such that by the time we're up in space making observations, the temperature's risen to the temperature range we desire the instrument to be to conduct the observation. And it's only making the observation for about 10 minutes, and then it comes down. So nothing's perfect, but we thought about that. We designed for it. We try our best to mitigate any issues. And so far, it's been fairly consistent in hitting that temperature range at the point of observation, the time frame of observation.
Other questions? Yeah, go ahead.
I have a question. I saw a little term up there, heliophysics. And you were saying that your rockets go up there and you have 10 minutes to do your observations or whatever like that. So my question is one of the goals of heliophysics to be able to determine, to predict when these solar flares will happen, instead of, like you were saying, you wait and then you shoot them up. So is one of the goals to be able to predict so you could shoot them up? So right when it's happening, you can observe that.
So trying to repeat the question online. One of the goals of heliophysics is to predict when a flare happens and to have the rocket launch in time so that it catches the peak of the flare. Is that good enough? Yes. So the word helios, no, it's Greek for sun, so it's heliocentric, right? So we're studying the sun, the heliophysics, sun physics, heliosphere, sun sphere.
Then I have another question.
Another question.
And my other question is that when you shoot these rockets up, right? Is there, and then you were piggybacking up to put a satellite to the space station and then have them shoot it out into orbit for you. So what is the, the protocol when you're dealing with rockets and you're dealing with people that are getting your stuff up to the space station? So how does all that happen?
So try to repeat the question for people online. What's the protocol for rockets compared to CubeSats? Can you be more specific again with the astronauts?
Yeah, as in, who do you talk to and how do you get the resources or how do you get permission to have your stuff go on the rocket that goes to the space?
Okay, so who do we talk to get formal approval and licensing to do these things? For the most part, we write proposals to NASA. It's not always this case, but one way is to go through NASA, and NASA works through that process for us. They already have a system that's streamlined to make sure that everything we put onto the ISS is suitable and safe for the astronauts. So our CubeSat had a series of checks that it had to satisfy. A very important one is our first CubeSat, Minx 1, was at low Earth orbit at an altitude of the ISS, which is roughly 400 kilometers. At that altitude and the density of the atmosphere of Earth, we have drag because we don't have any thrusters to change our orbit altitude. So we eventually deorbit and we burn up in Earth's atmosphere. One of the critical things we had to ensure NASA of, and they checked for this, is that we could not have very dense components that were very large, such that they would not burn up upon re-entry into Earth's atmosphere. An example of that is in the aperture, the opening of our X-ray detector, it's tungsten. So we had to ensure that the tungsten was a small enough size because it's very dense that it would disintegrate in the atmosphere. So that was a check that we had to satisfy for NASA. That's a safety precaution. They don't want pieces of metal flying and hitting people in cities, basically. For the rocket, there are many checks. I mentioned one rocket was cut down, and that's a safety protocol. And White Sands Missile Range, one of the rockets that did have one of my PhD projects on it, went off the rails the wrong way. There's gyroscopes, and they tell the rocket kind of where to point, helps it balance. All I'll say is there was a person that was a new hire, put it in the wrong way, 90 degrees out of phase. There's nothing that we could, as a science team, could have done about that. That was the rocket booster team. And it went the wrong way, and they terminated the flight, separated the payload from the booster. No science data.
My last question is that the rockets launch, you get your 10 minutes and they come back down and they parachute down. And so you have these rockets. Is there anything that you reuse on those rockets? Is there reusable stuff that you use, materials or stuff in the rocket that you reuse? Or is it all just, you check it out and go over it and then build new stuff for the next one?
So summary of the question for people online, do we reuse any of the components for the sounding rocket, including the rocket itself and the scientific payload? Yes and yes. Scientific payload, most of the time, the scientific teams, they want their instrument back. I definitely wanted part of my science instrument back when I was working on it for grad school. And we do that by having a parachute and a series of protocols to ensure that the payload returns safely. Primarily making it robust. This is mechanically, structurally, and orienting it in such a way that when it does impact down, it doesn't destroy vital components. That's difficult to do. That comes through with a lot of testing to ensure that that's the case, number one. So that's for the sounding rockets. For the boosters, for the scientific payload. For the boosters, they reuse the company's called NASRock. They reuse the boosters almost every time. And that's pretty smart because that saves a lot of money. They were doing that before Elon Musk was doing it. But Elon Musk, his goals are very different. And those rockets that he's doing are much, much larger. And they're going much farther out into space. But yes, we try to reuse the whole thing.
Let me share a question online here. Brian Rosenblatt says, great talk. What is the main source of the UV light emitted during solar corona, and do they also emit X-rays?
So I believe the question is, what's the source of UV light?
UV light during the corona, and is there also X-ray emission?
Yes, there's also X-ray emission. I showed the photograph that we took from space from the Hinode X-ray telescope of X-rays from the sun, and how it varied over 11 years, where you saw a bunch of sunspots or active regions and then not many. The sun makes the UV light, it makes the X-rays. It's the hottest gas for the most part that generates the ultraviolet light and the X-rays. You can also have X-rays come from highly energetic processes. So when the solar flare happens, the solar flare itself are magnetic fields rearranging themselves. And when they do that, they accelerate charged particles. That whole process also generates hard X-rays and soft X-rays. But that's not a temperature dependent process. But most of the X-rays and ultraviolet light is coming simply because the gas is very, very, very hot.
Other questions? Yeah.
What we're trying to figure out is, why is the gas so hot? That's the Nobel Prize winning type of question to be answered.
Let me get Leia in the back there.
Yes. Well, initially they make aurora. The particles that are slingshotted towards Earth eventually can come and travel along Earth's magnetic field lines. And these magnetic field lines, they go into Earth's atmosphere mostly in the northern and southern poles, the magnetic poles, not necessarily the geometric poles, but they're pretty closely aligned. And so that's why in the northern lights, the northern hemisphere and southern hemisphere, they tend to see aurora. There were some pretty strong magnetic field disturbances from big flares that happened around April and March of this year. So people up in Massachusetts, like where I live in Boston, Cambridge, could even see some northern lights. In addition to that, if you have a significant and strong enough storm, you can have devastating impacts on satellites, particularly communication satellites. Now, things have happened. There have been many improvements over the past decades where that's not as big of a case. That used to be a big issue. There are also power lines that could be disturbed from induced electric and magnetic fields from the influx of particles. Again, these aren't as big of issues as they used to be 30, 40, 50 years ago, because a lot of changes have happened to the infrastructure to mitigate that. But those are some of the immediate Earth-like impacts. Now, as we move on to this new phase where we're trying to go back to the moon, go to asteroids as humans, go to asteroids and then go to Mars with these astronauts. The big question is how well we can predict when a flare happens, and then what do we do to safeguard the astronauts when they're in space when this does happen? If you're out doing a walk and you have a whole bunch of X-rays coming, that's a problem for an astronaut. What's a bigger problem are the energetic particles. They're called SEPs, solar energetic particles, and also the coronal mass ejections, if they're directed towards these astronauts when they're on the spacecraft and they're outside of the protective magnetic field of Earth. So that's the moon, those are asteroids, and that's Mars. I go to a lot of schools, like grade schools, and talk to kids, and they always say, do you want to go to Mars? Because I am interested in becoming an astronaut one day. I'm getting older, so maybe it may not happen. I'm just saying we had a conversation, I'm getting older, right? So it may not happen. I do know some astronauts that are 50 years old when they went to space. I'm in my 30s, so I still have like 20 years to go. But, time's running out, right? But I want to go to the moon, but not Mars. Because I know too much about solar physics. I don't want to be outside Earth's magnetic field too long on that long journey when some big eruptions happen. I just know too much physics, right? So I'll leave that for other people that are brave enough to do it.
That's a good question. Let me get this fellow right here.
That is the solar winds and aurora. Is that why you watched that during Alaska? I was just curious, like, why did you choose that location versus like something closer to the equator?
So the question is, solar winds, and also,
Why did you launch at Alaska and not like somewhere closer to the equator?
correct. The reason I mentioned solar wind, because I want to define it for everyone here real quick. So he mentioned about solar wind, which is another phenomena. And he also asked, why did we launch in Alaska? Did we do that on purpose? Was that our goal? Solar wind is a constant stream of particles that come off from the sun. All stars have a wind, similar to what you feel here on Earth. You really can't see it easily because the particle density is so thin, but you could definitely feel it. One cool thing is solar cells, solar sails. There's a concept that we could like use the particles flux from the sun to have small satellites drift into space. So I think that's actually a pretty cool idea. But stellar winds exist. They're pretty cool. Did we want to go to Alaska on purpose? No. It was cold. Alaska's cool. But as we're in the mountains in the middle of nowhere. We saw moose, saw some bears, which was cool, but being there for that long, we prefer not to because it was really cold. I'd rather be in a desert than at like 0 degrees outside in the mountains where there's no one to help you if something happens. We had each other to help each other. The reason we were there is because at White Sands Missile Range, I believe is US 70. There's a major highway that goes towards the White Sands National Monument. You basically cannot close, as of currently right now, close that road down for any more than I think 30 minutes at a time, maybe an hour. I think it's an hour. And our goal was to sit and wait for a solar flare to launch. And when we're sitting there, we're armed. There's a whole 3-hour process at check that has to happen every single morning once we go vertical to make sure that everything's triggered and such that we have T-3 minutes. So a decision is made, we want to launch. Okay, T-3 minutes starts, and then we're doing the final checks. And there's a hold at T-1 minute for the final go, no go across the board for all the teams. And so that's like a 3 to 5 minute time frame. And then we're launching. So they wouldn't let us sit there and do that all day. So they said, you can go to Alaska because there's nobody in the missile range. So that's why we went to Alaska. It was all like, again, all for science, right? We're doing all this just to study stars.
Do you want to ask your question? Yeah.
What are the 2 parts that are coming out from the space station?
Those are 2 CubeSats. One is the CubeSat that I worked on, which is the second one. And the first one is another CubeSat from another university. So sorry, I didn't repeat the question for the person previous to this question. That person asked, what are these 2 objects coming out of this deployer from the International Space Station? Now, the question I was just asked is, do I have any advice for someone that's in high school? That's in high school that wants to go into astrophysics or physics? Someone in the audience said, go to Boise State. So you can go to Boise State, try it. Work on your math skills right now and your critical thinking, analytical skills. That would help. But at the end of the day, you truly, in my opinion, truly won't know the nuances and the complexity of physics and astrophysics as a study until you do it, start doing it. So all I can say now is just work on your math skills. This is calculus 1, 2, 3, differential equations, linear algebra, things like that, if you can, to prepare for your first year, your freshman year of undergrad as a astrophysics major. And then you'll find out if you really like it after your first couple of years. But the math will help you. Because all physics really is applying mathematical models and methods to try to understand the physical world around us. In a nutshell, that's the simplest way I can try to describe physics. And then astrophysics is applying physical laws and principles to astronomical objects.
All right, maybe one more question. I'm gonna give Sasha the last one. Go ahead.
So the question is, do we manufacture the solar panels ourselves? For me, particularly, my role again was instrument scientist for the CubeSat. So as part of my PhD work, design, development, modification of the detector, science analysis, etc. James Mason was the other PhD student. He was an aerospace major. He was in charge of the solar panels. We procured the physical panels. They were tested individually, separately for quality. and then they were inserted on the spacecraft, and then the wires were also assembled and connected and run out. And then we tested it on the CubeSat as you saw. So we didn't physically modify the silicon and build the circuitry on it, but we acquired it, tested it individually, placed it as a component, and then tested them as a system. The next follow-up question was, are the solar panels in a similar type and composition as the ones used on Earth? For the most part, yes. There are differences to make them space flight quality, but for the most part, yes.
Okay, with that, let's thank our guest speaker again. Have a great weekend, and let's see you in March.
Thank you all again. It was fun.